So first of all, I'd like to thank the organizers for giving me this opportunity. Hope you can see my slides properly. So today I'll be talking about work that I've done with Joe Bowie, Gwendolyn Edie, and Sebastian J. Mungal at the University of Toronto, where I'm a PhD candidate. So first, I'd like to focus your attention towards the intrinsic dimensionality of spectra and what prospects it has for galactic archaeology. So Yuan Senting already gave a great talk on a similar concept, so I'll be talking about a little more of that. So the motivation behind this project is that we have stars that form in giant molecular clouds. These groups of stars or star clusters are expected to be chemically homogeneous because of turbulent mixing that happens in these giant molecular clouds early during their assembly. These stars die, they enrich the interstellar medium with heavy elements, and this is sort of the simple picture of chemical evolution we have. But we know that this whole process is actually very complicated. There's a lot of elements that go into it. And it's crazy that we know so many of the steps, but there's one particular step here that I want to focus your attention on, which is how does the intercloud medium in these dense molecular clouds actually mix and evolve, and how does star formation proceed in these clouds? Can we assume that these are chemically homogeneous, or maybe type 2 supernovae cause some pollution in these molecular clouds during star formation, and that could add some level of inhomogeneity. So we actually want to study whether these open clusters are truly homogeneous or not. And when we assume that these are truly homogeneous, and we put them in the context of galactic evolution, we know that they get disrupted over millions of years due to gravitational interactions and radial migration in the galaxy. So we want to be able to actually chemically tag stars back to their birth radius, similar to a lot of other sort of interesting talks that have been there on chemical tagging. So how do we actually do this? We have a bunch of stars or a large number of stars in the galaxy where we can actually measure spectra. Right now we are using APOGEE, but in the future we'd like to do an analysis like this on Gala. And what we're doing is that taking one particular open cluster and measuring or inferring the chemical signatures of each and every star in this cluster. We want to see whether they are homogeneous or not. And one thing I'd like to highlight here is that this Bayesian context of posterior equals likelihood into data, prior, there's one step here, which is the likelihood, which is always or quite often assumed to have a particular form. Like it is common to have things like Gaussian distributions to assume a likelihood. But in terms of spectral data, we know that the likelihood has a lot of complications, like the line spread functions for the different absorption lines have some non-Gaussianity, and these LSFs can be variable, and also noise can be very correlated. So we cannot assume a form for the likelihood. So that's one thing I want to mention because I'll be coming back to it later. Now, when we actually want to infer something like this, we have models or the theta, which are the parameters, and our data. And there's quite a bit of gap between this. And this was recently termed as like the synthetic gap in one of the papers. And the idea is that our models, which have quite a few parameters, 10 to 40 parameters, are known to induce systematics because of things like assumptions and missing physics. We often assume one-dimensional, plane parallel, static, LTE atmospheres with fixed atomic data, which we know add some systematics. And the data we know is high dimensional, on the order of 10,000 or so in APOGEE. And there's a lot of instrumental factors that go in here as well, like telluric absorption lines, persistence, and so on. So, and there's another level of systematic that gets added, which is the pre-processing systematics, which is things like continuum normalization that can affect your uncertainties quite significantly. So what we wanted to do was we wanted to try and see whether we can remove as many assumptions in this process of inference as possible. And for that, we use something called the sequential neural likelihood. It's a likelihood-free inference procedure. That is, this goes back to how the likelihoods are not known, and we want to estimate what the likelihood of spectral data is like. So first, I'd like to focus your attention towards the inputs to this procedure, which is that we give an observed spectrum to our procedure. We give it a simulator, which tries to simulate spectra, which are as close as possible to the data. So essentially, this is like a simulation of a spectrum from a model atmosphere with added components like noise and what we understand about the noise. And then we have a prior where we've assumed uninformative priors. That is, we assume that we have this uniform prior on most of the parameters, these 15 parameters that we're using. And once this goes into the second process, now we are trying to estimate what the likelihood is like given these simulations. So we get these samples of theta, which are sampled from the prior, and the corresponding simulated data, which comes from the simulator. And then we try to compare that to the data in the next few steps. But we found out that when we wanted to compare the data, there's a lot of inefficiency that gets added because of the fact that our data has about 7,214 dimensions. And that's where we actually came into this domain of how do we want to find the intrinsic dimensionality of spectra. And here we are doing dimensional reduction using FPCA, or functional principal component analysis. And so I'll talk about why we use this particular method and how it's useful. So the issue was curse of dimensionality, as I talked about before, which is often referred to in machine learning as this idea that the more dimensions you have, your inference or likelihood-free inference is going to become more and more difficult. And the reason we use functional PCA is because functional data allows you to assume that each and every spectrum is essentially a continuous function over wavelength. And what that means is that, thank you, we can assume that each spectrum is a point in functional space rather than considering it as multivariate data. And this is what we take here, which is that the Y and M is the discrete observations, and they come from this functional form of lambda plus some noise. And what we do is to go from discrete data to actually these functional continuous forms. We use a linear combination of a set of basis functions, where the basis functions are these phi k's, and find what the functional form for each and every spectrum is like. And the trick here is that in this sort of procedure, the basis functions we use are synthetic spectra. And if we use a large number of synthetic spectra, it makes sure that the functional form is good. But at the same time, it makes sure that you don't include features like systematics and noise, which might not have wavelength dependencies the same as synthetic spectra do. So this tries to find the intrinsic dimensionality as good as possible. And then after we find this functional form, we do PCA in functional space using something called the mercers theorem. And the advantages of a procedure like this is that it adds continuity degree of smoothness and also domain knowledge into the PCA framework. And just to give you an example of how this works on a simple case study of just 10 spectra and 200 wavelengths, we find that the first 3 principal components for a case study like this is shown on the top for FPCA, and a similar thing is done for PCA, principal component analysis. And we find that this procedure does actually smooth out these noisy features quite significantly. And another thing we found is that if we simulate a systematic, so for example, here in black, we've simulated continuum normalization error. And we find that FPCA is capable of removing that, but PCA is not. And just to give you a visual representation of what this looks like, previously something like this was done with EMPCA, which is expectation maximization PCA. It just adds noise and missing data into the framework of PCA. And we find that the principal components look like this. And from PC8 to PC10, you see these like large scale features that we don't expect from theoretical variations. These are due to things like persistence. But when we do the same procedure through FPCA, we find that all of these features do actually get removed. And doing comparisons in a statistical form, we find that a lot of the intrinsic features we expect are there. And this is where the intrinsic dimensionality comes in. We tried to find what the dimensions are like, and we found that 10 components are usually required to reconstruct up a spectrum. So here I'm showing a reconstruction of a spectrum, and I want to highlight 2 things here. In the top, there's the data with an overlaid plot of the reconstruction, and on the bottom, there are residuals. And to the left, you can see that there is some sort of weird residual feature in the blue region, and that's actually the location of a known diffuse interstellar band. So while we can't tell for sure whether it is removing that because of an extrinsic feature, but it is doing that. And the second thing that I want to highlight is that because of this functional procedure of wavelength dependencies, it's able to generate data for masked regions quite well. And finally, this is the final part of our procedure, which is once we put these dimensionally reduced data and train these neural networks to learn what the likelihood of our data is like, then, and if we do this procedure on a large number of stars, so here, large number in terms of an open cluster is 28. So for 28 stars, I've estimated 15 different elements, and here I'm showing just the iron marginal. And if we combine all of these in a hierarchical framework, we find that the scatter is about 0.016 for iron. And essentially, now I would like to stop with the takeaways, which is that we found that FPCA is capable of extracting this intrinsic dimensionality of spectra. And it is really powerful for direct comparison of spectra as well. So we could use it in that framework rather than doing inference. And finally, we also introduced SNL into this. So thank you.
Great, thank you very much. I'm gonna do a quick clap and also a reaction clap to that as well. We only have time for one question. Ella Wang in the chat asks if there are systematics in every synthetic spectrum would these propagate through?
So yeah, if we do add systematics in the synthetic spectra, we expect that they would show up in the FPCA framework, just because the synthetic spectra or the basis functions are what we think are the variations we expect in the data.